but I do want to point out that we don't have a lot of new material to go over left. What that means is I'm going to be probably this weekend working on trying to get together the student projects, and either next week or the week after we're going to begin the projects. Okay? And it's going to entail, I have some sources I'm hoping to get some very real world data from that we're going to work with. And what we're going to essentially try to be doing is putting everything together. Kind of the big picture, very hands-on. I'll be there to help at every stage. But I just want you to be aware that that's coming up probably before by the beginning of November. And so you'll have about a month to complete it. And depending on the data sets that we end up with, there will be a bunch of pre-processing. If you remember going through the pre-processing steps at the beginning of the semester, aligning all your data, filling in possibly missing data points before you even put it into a format for the different algorithms that we have. So just the end of kind of the new material that we're going over is in sight, and then it's going to be your turn to really dive into the material, figure out what's going to probably be some of the hardest steps to do is going to be a lot of that pre-processing, getting the information in a form where we can actually use it. Yeah?
Are we going to be learning Moses outside of class with you?
Yeah,
okay.
For us.
So we're going to be meeting a separate day.
Right.
Okay.
Well, and the other thing that I will mention, there probably next week will be, there will be some more new material, but it's going to be more specialized advanced techniques and so on that you may or may not be using in your projects. So does that answer your question?
So you don't have the details of our projects?
Not yet. I'm going to be, I've been working with a colleague of mine, and he's been incredibly busy as well, so, but I'm going to hopefully be talking on the phone with him this weekend and that. And that's just some of the data sets, not all of the data sets, depending on the project. So, any questions about what we're going to be doing moving forward in Daytona? Your mic is... Questions in Daytona?
Yeah. Is that a team project or is it an individual project?
We will, that's a good question. I'm thinking that what we will do on the projects is the first part of each project. I haven't developed them completely yet, but will be partially individual and then combining those efforts into teams.
That's wonderful. Okay, that's a good idea.
So starting off, each person doing a separate piece of it, and then, but I have to work out all those details.
Yeah, how are you going to separate? Are the pieces going to be similar as?
I have to work out all those details. And it's going to depend on the actual data sets that I end up with. Okay. Other questions? Daytona? Yes.
Yeah. I have a comment.
Yes.
The special scope, I think, is start from individual project is better than each one and a different type of algorithm. And then when you merge, you have the same data set, but have different algorithms to see which one is the best.
Oh,
Then
that's-
you want to put it together to see which one works for the best for that problem.
That's an interesting idea, yeah. That would be,
Yeah, somebody go maybe, yes, network, somebody go decision tree, and they are different. But you will merge, then they're going to really have the analysis. If they argue which one is better for this one and why.
okay, yeah, that's an interesting idea. And that might be how I proceed. As I say, I haven't gotten all the data yet. And so a lot of what we're going to do is going to depend on exactly what that data looks like.
You just need a few sets because there's a few teams.
Right.
Each team will
Right.
share the same set.
I'm thinking we're going to have 2 teams here and maybe 1 team there.
Yeah, that's a good idea. I think so.
So I'm going to be investigating a lot of that, talking to my colleague and looking at some other resources. Questions here or in either location? Okay. So,
What did Jeremiah?
on Wednesday we looked at clustering. We began the clustering module, and we looked at one particular algorithm, and that was, anybody remember the name?
K-means.
K-means. And did anyone have questions on the basic principles? Not so much the nitty-gritty details, but just how the algorithm worked in general. We're going to look at a couple more algorithms in clustering, but they're all we're only going to restrict ourselves to 2 more, and they all share a lot of similarities with that k-means classifier. So, any questions in Florida?
Yeah, okay. No questions here.
No questions. Okay. Then I'll pick up by beginning the next 2. You know, I think the...
James doesn't.
I don't know what time. You guys are also.
So, as I said, there are a couple of algorithms additionally that we're going to begin looking at today for clustering. And they share some similarities with k-means, but not everything obviously is the same. The first algorithm we're going to look at is going to be an example of what's called a statistical model. So the particular algorithm we're going to look at is called expectation maximization. And we'll see where those terms come from as we go through the algorithm. It's unsupervised clustering method. That means that no training is going to be required. It's based on a concept, and we're going to see this in the next slide, of what are called mixture models. And the underlying principle of the algorithm is it's going to attempt to find the most likely. In the technical term describing most likely is said to be maximum likelihood estimation. And basically we're looking for parameters of the underlying distributions. Again, hopefully on the next slide this will become a little bit clearer. So, and with luck this will move 1 slide forward. And it did. So here's an example of what we mean by mixture models. And so here you have these graphs here. You have two, these are basically a combination, for those who've seen some sort of probability or statistics, of what are called normal distributions. So the model here could be an example of two normal distributions corresponding to heights of, say, males and females. You have you're going to have two different peaks.
Okay.
Right? And you see that in the pictures. In this particular graph, they both have the same standard deviations, though those could also be different. And you notice that the means of the two distributions are different. So if you think of, has everyone seen at some point a bell curve, a normal curve? Basically, you have many different normal curves. Each one has a different average or mean, and that's what's being reflected here. They also may have a different spread. They may be spread out less or more. And what we're doing here is really mixing two distributions together. And this would be an example with exactly a mixture of two distributions. You could have mixtures of more distributions. And what you're going to do, how the algorithm's going to work is it's going to try to adjust the various parameters for each of the distributions. The parameters being the mean and the standard deviation, the measures of the average and the spread. Is that? Okay. Until you get the most likely scenario to fit the data that you actually have. And that's going to then cluster your data into the different groups.
Can you have more than one peak? Or is that only two?
For
mixture models.
Well, so you can actually have different types of distributions.
Oh.
Okay? I use the normal distribution. But you could have, you're in probability and statistics, you could have a gamma distribution.
Oh.
Okay? But then you've got different parameters that you're going to have to adjust. Or you could have a uniform distribution.
Wouldn't you have to use the same distribution for each, I don't know, I guess.
It would probably be easier.
Right, because then you wouldn't have to look at the differences.
And in practice, if you look at WECA's implementation, it's strictly looking, that I noticed, at Gaussian distributions.
Okay.
But there's nothing in the basic underlying principle restricting you to that. So here's how, here's really the pseudocode for the algorithm. So you're going to choose your initial set of parameters. That could be randomly or something
given here.
just to get the system started. In the previous slide, you might do some, ahead of time, you might look to see if you can see anything, some visualization to help guide you along the way. And here, we're looking at Gaussians. You might, if you presume that you're looking at Gaussian or normal distributions, you're going to choose two means and maybe the same standard deviation or maybe two different standard deviations in this example. Okay. That reminded me. So now the loop is going to proceed fairly straightforwardly. Okay. The first part of the loop is the expectation step. You're going to take each instance, each data object, right? And you're going to calculate probability. So this is why it's a statistical method for under your assumption of your parameter settings, the random parameters that you started with, that your instance belongs to each distribution. Okay? And then you have what's called the maximization step. Now you're going to find new parameter estimates. You're now going to change the parameters to try to maximize all of your expected likelihoods. To maximize the probabilities that your data fits. So you're going to adjust the distributions to get a better chance, a better probability that your data is matching the distributions. And you're going to repeat this process. You readjust your probabilities, and then you adjust your distribution. And at each step, you're trying to see, you're calculating your probabilities, so this is going to shift all the probabilities after you maximize your parameter settings to update your next set of probabilities.
So you keep doing that until you find
until you have some sort of convergence that your parameters aren't changing very much at all.
Does the number of times you repeat it, like,
I don't know.
dilute the information you're getting? Like,
Well, you're going to do it until your parameters are fairly constant.
okay.
I don't know if that's what you were
Yeah.
asking.
Yeah.
So some comments about this algorithm. In some ways, it's actually a generalization of k-means. I mean, I mentioned that there's a lot of similarity here. In fact, if you look at Euclidean data, so distance data using our normal distance measure on spherical normal distributions with technically equal covariance measures, but your means might all be different, then your expectation step is almost the same as the k-means cluster assignment, with one difference. With k-means, an object goes to one cluster or the other. With probabilities, you're going to kind of assign an instance with a probability to each cluster. So, and there's really a difference. It can, a particular instance is actually assigned to both, if you have two clusters, to both clusters just with different probabilities.
Right.
And your maximization step corresponds to what we did with our centroid calculation. After each step, after you've made your reassignment, right, in k-means, if you remember k-means, then you update your center of mass of each of your points, of each of your centroids, or the position of each of your centroids. So some disadvantages.
Slow.
It's comparatively slow.
Compared to what?
Say k-means. One of the big, actually, disadvantages is if you have high dimensional data, you end up it doesn't tend to work that well, and because of just the numeric precision involved.
It's not very precise.
It just
It's too.
it fails. I mean, you're trying to get too much numerical precision and things just go haywire. The other thing, and I mean, it's actually in some ways an advantage as well as a disadvantage. You have to choose the model type, whether you're going to choose a normal distribution or a different kind of distribution. But that can be useful. I think I skipped a slide. That can actually be an advantage if you know your data might have some interesting behavior, and you can model that knowing the type of distribution that it is.
So what does the distribution, what would that change?
That would change your shape of your clusters.
Okay.
So with a normal distribution, you have a bell curve.
Yeah.
But you can have other kinds of distributions, which gets to, I think, James's question earlier. In principle, you can have different distributions,
Yeah.
but do the same expectation, calculate the probabilities, assign them. I've not worked with that, so I don't know how well that works in practice, but does that, so your distributions could have different shapes.
Yeah. I didn't see what, like as long as they're all the same distribution, I would expect.
Right, but you see, in a normal distribution, you're going to have like a, well, let's bring it up on the whiteboard. I always forget which one it is. That one. So with a normal distribution, you're going to tend to, right, because the normal distribution, a single normal distribution is this generally bell-shaped curve.
Yeah.
Right? Well, that's kind of restricting yourself to a kind of, if that's a spherical or ellipsoidal shape, that's going to, you can adjust the parameters to change the shape in different directions if it's multivariable. But in general, you're not going to end up with, in general, you're going to end up with more globular shapes, as with k-means, something along the lines of that, with your edges going down, right? Whereas if you have some more interesting or more some unusual shapes in your data, you might be interested in a different distribution.
Okay.
Is that?
Because it fits your data better.
Pardon? That fits your data better, right?
Okay.
Just in general principles. And I did have some. Where are we here? Oh, we're here. I think we were on advantages. And it can be an advantage that your instances, so here it is, can use a variety of shapes. Instances can be assigned to multiple clusters via some probability assignments. Now, I did say different shapes. It's not as general, it's still pretty, it's not as general as some other clustering algorithms, some density-based clustering algorithms that we're not going to cover. For example, with a density-based algorithms, you can actually end up with, say, clusters more like that, right? And maybe you have another cluster like that.
Mm.
Okay, so if you have clusters that with your maybe some pre-processing you kind of see or you suspect, because sometimes we're not able to even visualize our data to look like something like that.
Yeah.
So sometimes if you suspect that it might be something different, or you might just throw it out there. Will a density-based scan work better? for the particular data that you're looking at. Oftentimes you don't really know until you dive into the problem, which is why I want to make a very general project to where you can actually do this.
So kind of like what we did with our quiz, right?
Right, but it's going to be beyond. It's going to be more detailed than the quiz.
Right.
The quiz was getting you to understand WECA,
Right.
but now we're going to combine the whole process, right? From the start to finish.
So you're gonna have to run a bunch of different steps for our first.
You're going to be looking at pre-processing.
Yeah.
Take a look at visualization, if that's going to help us. Is that going to help us if we say, do want to use something like expectation maximization to choose a distribution that might work better, as an example?
Okay. So we're going to be looking through different processes for pre-processing. Going to look at the best.
The pre-processing is, for the most part, I was just looking online today because when I taught bioinformatics a few years ago, we were looking at these protein databases.
Okay.
And you get these flat files. But there's a lot of information in those files that we may or not be interested in. So we're going to want to strip out and keep only the data that we need, that we want to use.
Okay.
Now, how are we going to do that?
Right.
That's part of the pre-processing step. Then, getting the data from the format of the database into a format, if we're using WECA, into an ARF file so that we can import it into WECA.
Okay. So.
That's why we're going to have a whole month to work on this.
So.
And I'm going to be there helping each person. I want to be available to everybody, except for the 2 days I'll be gone. But
Yeah, it might be a little off topic, and I feel like we already kind of went through this. But when do you want to? When do you classify and when do you cluster?
okay, so the good question, right?
Mm-hmm. Great question.
So classification is when you're trying to determine whether something fits a particular category,
Okay.
a particular class. Clustering, you don't have a predetermined class that you're trying to decide whether something fits into that class or not.
Okay.
You're just trying to get internal structures that says, okay, here are different groups. Your data tends to coalesce into these different groups.
Okay.
Okay? Now, you could use clustering to try to guide you towards classification, right? Because you're seeing the different groups, and maybe you can identify a group that might be of interest.
So each group could have a different class.
Well, I mean, even when you're looking at classification, you've got all these different attributes in your data, all these different characteristics. If you think back to the weather example, you looked at the outlook, any one of those you could use as your class that you're trying to predict. Okay? But we chose the are you going to play class. Based on the weather, are the weather conditions something of interest for you to go out and play? That was a predetermined class. We chose that class. Okay? Does that make sense? And in fact, that I meant to do something else at the beginning of class today, but we'll come back to that. Either today or next time. So, slide. Okay, so that's expectation maximization. And I tried to, notice I stayed away from going into a lot of the details. The details we can work out later. But I wanted to show a lot of similarity in conceptual understanding between these various algorithms. And we have one more I want to talk about, but getting back to James's classification versus visualization question reminded me that what I really wanted to start with, so this would actually be a good time so we're not too algorithmed out today, although this will also be somewhat similar. I'd like to go back to Weka and start looking at some of the clustering and visualization that one can do after clustering. So but before I begin, let's check in with Daytona Beach and see if they have questions before we go into using some visual clustering for visualization.
I have a question. Alright. So you heard what he said he's going to not be in 2 days, right? Month, day, right? 2 class. What he said? Monday, Wednesday, right? He said that he's going out. So ask him if that question. You ask him over? Yeah. Can I ask what's that? He said he's not town. When, yeah. You said you're going to be out of town. When you're going to have no class?
That's not for a couple of weeks. So actually, I think 2 weeks from today.
Okay, that's when they stop their project. Okay.
Right. And then 2 weeks, and then the following Monday. But I'm going to be here all of next week, and then the following Monday, Wednesday. So I'll give a heads up notice when that gets closer.
Okay.
Okay, sure. Thank you.
Okay, so let's share the desktop. And let's bring in, I think this mouse problem is actually related to the smartboard. Because it was working fine before the smartboard came. And we'll bring up.
Blame it on the smartboard. Well, that's ridiculous. Like, why would we make that happen?
I guess we can use the old version of Weka. And let's go to the Explorer. I turn. And I'm going to open up. Where is that? Where are the
Program files.
right? C drive,
Yeah.
x86.
I think it was 64. Yeah.
There it is. Okay, this is the ionosphere. And I'm trying to remember, and we're going to cluster and number of clusters, negative one.
Yeah, what?
Trying to remember, maybe that means so we just loaded the ionosphere data, one you worked with on the quiz, and it's going through, I chose the expectation maximization, and it's going through some of the steps here. And so here it clustered it into 10 different clusters. The log likelihood is a measure, if it's 0, then it's perfectly clustered. But basically, you can always get that value,
Yeah.
right? By increasing the number of clusters to be the number of instances.
Right.
And just make every instance its own cluster, which basically defeats the whole purpose, right?
Couldn't you do the same thing by just making it all one big cluster?
Well, now, not, yeah, you want to, I mean, it kind of, except everyone's, you remember you've kind of got that centroid idea, so you've got probabilities of being in that.
So is 12, is that a pretty large number for this?
Well, I can't remember how many instances the ionosphere we could take a look at. So it ended up with, right, there's 313 and 38. So you're looking at like 350 different instances. So you're basically putting those 350 different instances into 10 clusters. So that seems reasonable. Does that make some sense? So now what we are interested in was it?
Oh, wow.
So now if I do this, right click on the, I think that's how I got this. Visualize cluster assignments, there we go. So when we do that, we're looking at the visualization of the cluster assignments. You're not going to want to ever use your instance number to see how the clusters form. And so what we're going to do is compare, say, your A5 data. Why did it not? There we go. With some other direction. A couple of these, you can start to see the clusters forming. Right here I'm comparing, that's an instance number. If this mouse ever works.
Now,
Oh.
go in the center.
Hey, if you can't find the center, that's the best mouse stone.
So you can kind of see the clustering. So this is, you're basically looking at different attributes against each other. These are just some random attributes here. You can adjust them also by doing your X along the right-hand side. But notice there you've got the clusters are in different colors. And so the dark blue cluster is cluster 0. And you can kind of see the cluster forming there. And the black cluster is cluster 9, and again, that's kind of up and to the right. So this clustering, getting back to kind of James's question about what's the difference between clustering and classification, I gave an answer to that. But I often will look at clustering just to help me, as much as anything, understand, to see if the data itself is grouping itself. And that can be a guide to helping do some classification as well. What are going to be what attributes might I be interested in classifying something as? It depends on, again, it's going, the upshot in data mining is always know what your data looks like. Try to really, especially when you've got big data, it's hard to grasp it because it's just huge. But you can use all these different tools to try to get a better picture of what it is you're looking at. And the more you can understand that, the more you know that different tools might be useful or not. Know the problem that you're trying to solve, know the data that you're looking at. I mean, that's what it ultimately comes down to. I don't know, did that help at all?
Yeah.
Put things into perspective. And then, as I said, you can notice the X and Y labels here. We're looking at this value for X and this value for Y. I can shift my X, say, down to that value. And notice now your clusters, you're looking at different dimensions. You're looking at one attribute versus a different attribute now. I've changed my X attribute. And again, your labels down here. So here your X attribute looks like it goes from -1 to 1. And I'd have to look at what number that attribute is to understand what that corresponds to for the ionosphere example.
Yeah. How do you do that?
How do I do that? Well, that goes back to, I think in the, first of all, you have to make it so I can see the screen.
Gosh, this mouse is just...
Okay, so here I'm looking at X12 versus A12 versus A9. I think on the ionosphere example, it didn't really say what those points were, but you could look at your original data set, right? Your ARF files. I think that
Okay, so we have to look at the files.
well, that's one way for sure. I don't think that's the only way. So here's the original file. I mean, you could do it within Weka too, but I think it said maybe at the top what the different attributes were. But I think in this case they just called them A0 through.
Yeah, and then once again, it's like, looking at that, there was nothing for me.
Well, I'm going up to the top, which is where it went. So it just said, yeah, here they are, here's your attributes. They just call them A01, A02. In general, you're going to have different labels for that, like weather, like rain, humid. You can have your own labels, length, width. So if you're interested in doing it, so this is kind of a toy problem. So they just did the, they just gave you A01 and so on. Okay, so I think we'll quit there, and let me bring up the.
They bring your phone to weekends, right?
What?
They bring your phone to weekends, right?
I don't really bring my phone when I go out, so.
stupid stuff like this.
Great, Pablo. Where's the fun in not doing it?
Questions in Daytona or here?
You need to go get my phone.